maybe I start. Is it okay? Okay. So I just remind you what I said before lunch. So maybe now I just say that basic strategy in Lagrangian Floer theory. So this is after the introduction part. So I always assume that these two Lagrangians are transversal in this talk. And then I have this CF L1, L0, and I have this delta here. And I remind you some moduli space like M of P tilde minus and P tilde plus, and J here. This is a J holomorphic strips. So this is actually the part of the complex plane, so that this imaginary part is maybe lying between 0 and 1. 2 X with three properties. One is J holomorphic condition, and second is boundary condition, and third is asymptotic conditions. The asymptotic condition from P tilde to P tilde minus to P tilde plus. And then let's suppose that this is a nice space, and then dimension of this moduli space is equal to the difference of index, type mass of index, minus 1. So this is okay. And so if so let's suppose this one, and if for when this mu P tilde plus is equal to mu P minus mu tilde minus is equal to, then this M of P tilde minus and P tilde plus is after union of R Q tilde, so that mu Q tilde is equal to mu P tilde minus plus 1, and then the product is, sorry, this is the boundaries. This is the boundary, sorry. Last time I forgot to put the boundary, and so this boundary of this one is equal to P tilde minus and Q tilde times M Q tilde and P tilde plus. If you have these properties, and also, yeah, one more condition. Yes. Sorry. One more condition is, so when mu of P tilde plus minus mu of P tilde minus is equal to 1, and then this M of P tilde minus and P tilde plus is finite set of points, which actually cut out transversally somehow. And if we have these, and then we can define this delta of P tilde by just a sum of number of points in this, and then apply this. Because it's finite, you can count the number of them. And then this one satisfies this condition. Namely, we get a boundary operator of certain cochain complex, right? So we get this C L1, L0, and also this delta, right? Certainly, this is not always the case, but if you have this, and then you have this. And then we define this Floer cohomology just by this kernel of delta over image of delta, right? So grading actually, if we, this CF has grading by mu, and so therefore this is a Z-graded chain complex, and then this also have grading. So this is a graded modules, right? So, but this may not be true, but if it is the case, it is true. And so what I said is in the case of Floer, actually he assumes this pi 2 of xl is equal to 0. And all case, actually he considers this monotone Lagrangians, and minimal mass of number is 3. And in this case, actually, they also consider the ground ring R is actually Z over 2Z. So actually, they don't really give the sign. Just look at this as mod 2 cardinality modulo 2, and then did it. The reason is that in general, this modular space may not have a compatible orientations. And then, even though you have this, actually it is this thing may not be as oriented spaces. And so therefore in general it is not. So I will come back to this later. And another small thing is that, so what I said is, what I discussed before is actually this one. This one. But how this condition is related to that one, right? But Floer case, actually he considered a case that L1 is a Hamiltonian deformation of this L0. So you have two Lagrangian like L0 and L1 somewhere. And then certainly if you start some point from here, there is a path like a phi of h of t of p. Yeah? Then the end point lies on L1, right? So you have such a path. And then consider the component of this path space of this. Yeah? So now maybe I denote it by L0, and then consider the component, path connect component containing this L0, right? This is a path connect component containing this L0. Maybe, yeah, I don't know, L0. And then you can actually identify this space to a based, so now I consider this. So you have this P L0, L1 of L0, and then map it into P L0, L0 by the following. So here you have some path gamma. So gamma is actually T goes to gamma T. Then the corresponding path here is T goes to phi ht inverse of gamma T. Okay. So this one is just the end point. So T equal to 0, it is identity, so therefore it's just gamma 0, nothing but some points on this L0. But if you consider T equal to 1, then gamma 1 is on this L1, but because it mapped by phi h1 inverse, so therefore it can map back to L0. So therefore this is a path from L0 to L0. And L0 is actually going to the constant path, right? It's a constant path at this P, right? Everything just phi ht inverse and phi ht P is equal to P. So therefore, here actually, it's actually the path space, but the path space from L0 to L0. And then the base point is just to this point P. So here, base point may be just this path, but here is point based on P. Then you consider pi 1 of this thing at this thing, right? So if you consider pi 1 of P, L0, L0, which contains this point P, component containing constant path P, and base point P, right? And then this one is actually isomorphic to this pi 2 of x0 or something, right? Basically. So therefore, in this case, actually, in this special component, somehow everything governed by this pi 2 x0. So therefore, so Yongen also put some condition on pi 1 of Lagrangian in order to do something similar. But anyway, roughly speaking, yeah, this is just that's it. Okay, so this is just one supplement. So you have this. And then what kind of property do you want to have? So expected properties. So this construction certainly depends on the choice of almost complex J. And so if you have J and J prime for this. And then how they are related, right? So maybe I should denote by not just delta, but maybe delta J, because I use J here, right? And then this one can be infinite. This is infinite, but this you have an energy of this guy, it diverges to infinity. It implies that if you look at this value, I fix this initial point, and then look at the end point. The value of the end point actually diverges to infinity. So therefore, it stays in this. I forgot. It stays in this module. I define this as a half infinite sum. I allow the infinite sum so that this one diverges to infinity. So therefore, this is very defined if you have this. But anyway, so in these cases, probably you don't. No. In these cases, you don't really need to pay so much attention to this. But anyway, so for later purpose, I just made it. So in this case, then you have the CF and L0, L1, L1, L0. And here I have J. And I have two. Chain complexes. And modules are the same because I don't use J for the definition of module CF L1, L0. But the boundary operator is defined by using this, because this gradient trajectory depends on the choice of J. But nevertheless, we have a certain chain map between them, and they actually gives you isomorphism on cohomology. So actually they are chain homotopy equivalents. And another thing is that if you have phi of h, yes, maybe phi is equal to phi of h of 1, so that not only L1 is transversal to L0, but image of L1 is also transversal to L0, right? So we assume this one and this one. And then we can define the CF L1, L0, delta, maybe J, and here I have CF of phi of L1, L0 of maybe delta J prime. And then here, again, I have a chain homotopy equivalence. So this is actually a special case of this, so therefore, I don't really need to discuss this separately. But what I want to say is that for this one, actually, it doesn't depend, the cohomology doesn't depend on choice of J. And if I consider certain filtration on this complex and also filtration on the cohomology, then filtration doesn't depend choice of J in this case. And here, if we also have a filtration here, but this map does not really preserve the filtration. So I will tell it later. So this is the property and how we can see this. So this is basic strategy in Lagrangian Floer theory part. So maybe I don't need to discuss this part separated from here. But anyway, yeah. So let's consider that case. So we have maybe two ways to do this. So first I take J from there, but now I consider family of J. So that J tau is equal to J when tau is so small, and J prime if tau is so big, right? You just interpolate these two J's, because this space is actually contractible space, as I mentioned before. So therefore, you can always connect them by a path in here. And now, in this case, you have fixed Lagrangian boundary conditions. So therefore, when you consider this du d tau, and then I wrote that ju du d tau, du dt is equal to 0. This is the original equation for these Floer trajectories. But now I put here tau. So this is one way. And then, so this is actually J holomorphic equation, but maybe a bit modified by this. And then the boundary condition, in this case I don't move, so therefore I don't need to change. But in this case I have to move them. So maybe I can put it in two different ways. But the one way is just the following. So u of tau of 0 lies in this L0, but u of maybe tau of 1 lies in this phi of h of maybe I have to fix one function before. Like this. So where tau rho is a function like this. So this is a function on tau line, and so this may be like this. I don't know. Anyway like this. So here the value is just like 1, constant 1. Here the constant value 0, and something going on in the compact portion. And so this boundary condition is actually moving. So Lagrangian is moving. So we consider such things. And then asymptotic condition is the same. Okay, so asymptotic condition is the same. So I want to just write limit tau goes to plus minus infinity is equal to u tau t is equal to p tilde plus minus, and this p minus is the intersection point of L0 and L1, and P plus is a point in L0 and phi of L1. Endpoints are intersection point of two Lagrangians. If tau is so small, then I have L0 and L1. I don't really move L1, but if tau is so big, and then the Lagrangian boundary condition L0 and phi of L1, so therefore I can consider such asymptotic conditions. H is Hamiltonian. So So this H, right? Is this H?
Yeah.
So last time I considered this. And then from here, actually, we can cook up this Hamiltonian vector field HT. And then from here we can just look at this isotopy like this. So this H actually generating this Hamiltonian isotopy.
But J tau is also related by Hamiltonian isotopy, or just
This one, no, this is just a path. Yeah, you can also try to do something like this, but in this case actually these two are different almost complex structures, and in this case actually this phi no phi here. So here in this case actually, yeah, I just want to show that the resulting cohomology is independent of the choice of this, and so I need to pick up two different things. And here, this J and J prime also two arbitrary elements from here with certain transversality conditions. And so anyway, this is in this case a boundary condition moving.
you could have brought J to J tau as Hamiltonian. Is that,
No. Actually, in this case, actually, I don't really consider such things. I just consider two distinct J and J prime, or maybe yeah, two arbitrary J and J prime. But what you said appear, yeah, next. So this is one way to cook up this, analogous setting as this Floer trajectories. So Floer trajectories. I have this and this and this. But in this case, we also have another way to write it. So therefore, I just want to compare this. So I just erase it. So I mentioned the following. So if I have P of L0 and L1, right? If L1 is Hamiltonian isotopic to L0, then we can identify this with path space from L0 to L0. So now I also do the same thing. So here, maybe I have this, and then here I have L0 and phi of L1. And we can identify them. So the same thing. So if I have here path like a gamma from gamma is a path from T to gamma T, and then I map it to T to this phi of H of T of gamma of T, something like this, right? Then I take a covering space, both sides, and then try to compare the construction here and construction here. And then I get a bit different equation as follows. So this is du d tau plus j of u, maybe j tau of u, and then here I have du d tau, du dt minus x of, okay, so I have to have this rho t, so maybe rho tau and ht, something like this, of u is equal to 0. Sorry. In this case, I have to do sim. Sorry. This one is too quick. Yeah, I have to write this equation, but anyway. So here I just like a J holomorphic map equation, and here I have an equation like du d tau plus ju du dt is equal to 0. So this is a J holomorphic equation for gradient flow lines. And if you look at this part, and then the equation looks like this: du d tau plus j tilde of u, and here du dt minus x of ht of u is equal to 0. Yes. And this one, yeah, certainly I can take any almost complex factor, but somehow, yeah, as CA mentioned, somehow here you have this j, and then here we have another corresponding almost complex factor, so that this solution and this solution actually in one-to-one correspondence. I can tell you this a little bit later. And then the boundary condition. Here, actually u r cross I, r cross 0, r cross I is in Li, right? And here u of r cross, yes. Maybe I should do the opposite. I should do the opposite. Maybe I may be opposite. Sorry. This maybe I have to write it phi inverse or something. All right. Sorry. Sorry, so I start it again. Sorry, for this one. And then maybe I start from the other side. So here I consider du d tau plus ju du dt is equal to 0, sorry. And this side actually I consider du d tau plus j tilde u and du dt, maybe minus of this x of ht of u is equal to 0. Sorry, this way. So I just write in the opposite order. I think this is correct. And then here, the boundary condition here is that here after u cross r cross 0 lies in L0, and u of r cross 1 is in this phi of L1. And here u of r cross 0 is in L0, and u of r cross 1 is in L1. Okay? And then asymptotics. So in this case, so here, if you look at the 0 of this, so this is a gradient of this functional. So here the limit is somehow the constant path from L0 to phi L1, and here the gradient. If you look at the gradient for, then this one is equal to this vector field, right? And so this is the gradient vector field of some corresponding functional, and the critical point is solution of this equation, namely its so-called Hamiltonian cause from L0 to L1. So here we have a limit of tau plus minus infinity of u tau t is equal to this gamma tilde plus minus. They are actually Hamiltonian cause. And here, this one is limit as tau goes plus minus infinity of u tau t is equal to p tilde plus minus. So there are something. So we can actually, understand this Floer complex for L0 phi L1 just as this I explained here. But because path space can be identified this path space, and gradient can be also transformed to some vector field here, and then the gradient flow line also have corresponding object here, and then you have this kind of correspondence. So therefore, this is one-to-one correspondence. Yeah, like if you just have this solution here, then applying this one, and then you just write down the equation, and then you get this. Okay, so this is the case. So then in order to construct to CF of this phi L1, L0 stuff, this one, actually I can identify it with CF of L1, L0, but with this Hamilton function, namely generators are not a point, intersection point, but the Hamilton cause, and the Lagrangian flow line is not really the honest holomorphic curve, but perturbed by Hamiltonian perturbation term. And so from here, you have usual operator delta L0, L1, phi L1. And here, from here, you get this delta L0, L1, and H. And so here, operator here is just delta L0 and phi L1. And here, this is delta L0, L1, and capital H. So you have this. So they are actually the same chain complex. So then it is enough to have a chain map from here to here, so that it becomes a chain homotopy equivalence. Okay, and then instead of this equation, we can also consider following. So here, this is the boundary. So boundary condition, now it's a boundary condition moving. But if I consider this, then I don't need to move the boundary condition because this one has already fixed this one. So the boundary condition is the same. So like u of r cross 0 is in L0, and u of r cross 1 is in L1, right? And then asymptotic condition is a little bit different. So in this case, you take limit tau goes to minus infinity of u tau t. Maybe just certain lift of constant path at the intersection point. But if tau goes to plus infinity, the asymptotic is some lift of Hamiltonian cause, right? Like this. So yes. And then the holomorphic curve equation is also different because one equation is certainly this just du d tau plus ju du dt equals 0. And the other one is this. So therefore, we have to consider equation like du d tau plus this, maybe some other things of j tilde u, maybe depends on tau. And here I have du dt minus of x. And then I also use this function rho. And then multiply with ht. And then take u. And this is equal to 0. Something like this. So this is actually Hamilton vector field of x of rho tau times ht. So if tau is so small, then we don't have this term. So therefore, this is the Floer trajectory equation for this. But if tau is so big, and then this one is equal to 1, so therefore it becomes an equation like this. So therefore, at tau to infinity, we can see the gradual flow line in this one. And so either way, it's okay. So either you can use moving Lagrangian boundary condition, or maybe using this kind of Lagrangian is fixed, but equation is deformed by Hamiltonian perturbation terms. And either way, you can just cook up things. But the point is the energy estimate. So actually, as I said, so these paths are in one-to-one correspondence. And also solution of this equation, they are in one-to-one correspondence. But solution of this equation and solution of this equation is not exactly corresponding. So therefore, somehow bit different way to look up, but anyway, these two are. Okay, so in this case, we can also consider this energy, this side and that side, maybe also defined in this way of maybe better to just remove it because then it's easier. So I define this as an energy, and then when for Floer trajectory, U, we saw that this E of U is equal to this A of L0, L1 of P tilde plus minus A of L0, L1 of P tilde minus. So it is exactly this. But for these equations, but for this J-holomorphic prime or J-holomorphic double prime, it is not the case. So, but E of U is actually bounded by the difference, like A of L0 and phi L1 of P tilde plus minus A of L0, L1, P tilde minus plus some constant. Constant doesn't depend on the point, doesn't depend on the solution. So we have this kind of estimate. So therefore, if you fix these two endpoints, and then although this is not equal, this energy is bounded. So therefore, when you study the compactness property for the solution space, modulo this translation, no, in this case we don't have translation, sorry. The solution space, then this is good enough for control the limiting behavior as in the Floer trajectory case. And this constant is somehow related to the Hofer length of this phi of h of t. So maybe I can do some computation, but maybe I can skip it. Okay. So then we consider the following. So either way is okay. Yeah. For J holomorphic double prime, this is not this, but maybe A, L0, L1, and capital H, and gamma tilde plus or something, but I don't really want to write it. So this is okay, and then yes, and then what we want to say is this. So now we denote by n. N is a map from this U cross R cross L1 to X. We say this J holomorphic prime, and also boundary, maybe prime, or maybe this also prime, I'm moving superboundary prime, and asymptotics. So NP tilde Q tilde, sorry, N of P tilde minus P tilde plus. So we just consider such a space. And then we want to show the certain relations. So is it compact or not? And then the point is if P tilde plus is equal to mu of P tilde minus, then this N of P tilde minus and P tilde plus is a finite set. This actually coming from the transversality of this moduli space N, and also the compactness of this moduli space N, if it is zero dimension. So if it's a zero dimension case. Okay. So this is something similar as in the Floer trajectory case, but remember that here, in the Floer trajectory case, I have a symmetry by translation in the domain. But here it is not the case because this equation, maybe, even if you look at these boundary conditions, this condition is not really translationally symmetric. So therefore, if it is really moving, and then yeah, you don't have such a symmetry. If it happened to be constant, and then suddenly you have symmetry, and then we have to do something, and I will tell you it later. But now, okay, so this is the final set. And if it is one-dimensional, okay, so this, if mu of p tilde plus is equal to mu of p tilde minus plus 1, then what is happening is the following. So you take a boundary of this n of p tilde minus and p tilde plus. And then it is written in a very similar way as before, but here I have m and p tilde minus, and maybe I write it q tilde or something, and then here I have n of q tilde and p tilde plus, and here q tilde, in this case, is the intersection point of, q tilde has the index is equal to mu of p tilde minus plus 1, and this point q is the intersection point of L0 and L1, constant path. And then we have another one. So another one like this and this. Now first I have this n of p tilde minus and r tilde, and then m of r tilde and p tilde plus. So now r tilde has a, mu of r tilde is equal to mu of p tilde minus. So this is plus 1, but no plus 1 here. And then this r, this intersection point, is now in here L0 and phi of L1. So I have a solution somehow converging to this p tilde minus and p tilde plus, right? But here, actually, Lagrangian is fixed like L0 here. And here the Lagrangian is moving, so L of 1, but phi h rho tau, right? And then solution may split into two pieces, and solution split this side, right? And then this is p tilde plus, and this is q tilde here, and this is p tilde minus. And this one is exactly L1 and L0, and this one is same as this, phi h of rho tau L1, and this is L0. So therefore, this case, actually it's a Floer trajectory in the chain complex L0, L1, and this is solution of that equation. Or it may split into this way. So here it is L0. Here maybe it is phi h rho tau of L1, and here it is phi L1 and L0, right? And then here is r tilde, and here is p tilde plus and p tilde minus here. Okay. So we have two kinds of splittings. Bit different from the Floer trajectory case, because in that case, all the limits are the intersection points of L0 and L1. But here, some of them are intersection point of L0, L1, and some of the intersection points are L0 and phi L1. So therefore, these two cases. Okay? And then you count the solution of this equation. Then you get something, right? So now I define this phi from this CF L1, L0 to CF phi of L1 and L0. Okay, so I start from here p tilde, and then yes, map it to the following. So count the cardinality of this homogeneous space N of P tilde Q tilde, and then here I put this Q tilde. Right? In this case, mu of Q tilde is equal to mu of P tilde. It's the same, and this Q tilde is actually intersection point of L0 and phi L1. So certainly P is from L0 L1. So this sort of thing. And then, because of this first property, expected property, this is finite set, so therefore you can count the cardinality of this. And from a second property, we can see if you check the sign, and then you can see that this delta of L0 L1 prime composed with phi is equal to phi composed with delta L0 L1. Okay? So therefore, the first property gives you the well-definedness of this, and second property gives you this property. Namely, it's a chain map. So we have a chain map. Okay? So from here to here, you have a chain map. And now, we want to show that this one is actually homotopy equivalence, chain homotopy equivalence. But how we can see this? So for that purpose, we need to check two things. So one is the following. So in fact, I consider some way, right? So maybe, for instance, I have J tau, but maybe I have another J tau, right? So J tau is a path connecting from J to J prime, but there are so many paths, so therefore we may have several choices. And another thing is somehow you can also move. Wait. You can also move this. So like this. So you have phi, right? And you have phi h t. And maybe you have another one, like a phi of h tilde of t. So both are Hamiltonian isotopies. Both are Hamiltonian isotopies. So that's starting from identity. And end up with the same time one map. So you have several choices, right? And then maybe better to write with capital phi or something, capital phi. And from these data, you may get phi, maybe phi 1. And from this data, you may get phi 2. Both are chain maps. And how they are related. And in fact, they are chain homotopy equivalence. Chain homotopic, sorry. So we will see this. Is this okay? So just the construction depends on several choices. So therefore, we need to do this. And then another thing is, you may have concatenation of two Hamilton isotopies, right? So here you have phi h t, and then you have phi of k of t or something. You may have two things. And then you can concatenate them, right? So you have, from here, you can concatenate, namely, maybe you may consider phi kt composed with phi ht. Or there is a way to cook up some other Hamiltonian function so that some people like this way. No, this is the same. But anyway, like this. Then I denote by phi H1 is equal to phi, and here I have phi of k of 1 is equal to psi, and then here I have CF of L1, L0, and then I go to CF of first maybe phi of L1, L0, and then I consider next one like a psi of phi of L1 of L0. Assume that both are, all of them are transversal, and then we can consider such things, right? So phi and phi prime, right? But there is also a direct way to come from here to there, right? So using this, maybe I should indicate this. So using this, you get this, right? And using this, you get this, right? And using this, you get this. Okay? So just use first Hamilton isotropy to send this 10 complex to this 10 complex, and the second Hamilton isotropy just sends this one to this one. But you can also directly use this one to send this one to the other one. And then again, this is 10 homotopy, 10 homotopic. These two are 10 homotopic. Okay? So this is another story. And then another one is, how about identity? Yes? No, this is chain homotopic. That's chain homotopic. So on cohomology certainly there, but not much. This one, yeah, I can give you the formula from these things. There are many ways to represent this one. I mean, this one certainly, yeah, this same you put the same t, and then you can just write it in one Hamilton function to this. There is one way, and also first you travel with this, then you travel with this, right? So just 0 to 1/2, you just follow this one with double speed, and then follow this one double speed, and such a thing after homotopic to this one. And so anyway, so there are homotopics, then they are homotopic, and then yeah. Okay. Yeah. Then they are 10 homotopic. So anyway, so there are such things, and finally, this is kind of identity. So this is somehow mostly trivial in a sense, but if you look at it a bit carefully, then you may not be so comfortable. But okay, but I just want to say this. So you just consider trivial isotopy, like this always identity, right? So like just identity. So identity all the time, right? Identity from t equal to 0 to 1. So this is certainly one of Hamilton isotopy. And so therefore it must induce map like CF L1, L0 going to CF L1, L0, right? And this is identity in a sense. I have to be, yeah, in fact we have to be a bit careful, but why I say this? So I consider this moduli space N, and then I consider this one is actually U, so that is J holomorphic prime, and boundary prime, and asymptotic prime. But if this one is always identity, right? It's always identity, t equal to 0 to 1. Then I don't move anything. So therefore, this one is, as a solution, it is exactly same as the solution like a J holomorphic and boundary and asymptotic. Right? So this is actually our this M tilde. So where we have this R symmetry. And so here actually I don't really model by R, but here is R symmetry. And so therefore, yeah, so in this situation actually I consider zero-dimensional moduli space of this guy. In such a case, the solution must be constant. Otherwise, the action is free, so therefore the moduli space is positive dimension, right? Because I only consider zero-dimensional moduli space to cook up this, so therefore I consider zero-dimensional moduli space of this, and then that is constant. Therefore, it is identity. Maybe I can just stop here, but maybe another way of saying this is this. So I have a map from here to here with boundary condition and so on. When we consider this moduli space, we may just put any point, maybe just put this point like a 0, 1/2, or maybe 0, 0, or maybe 0, 1, anything is okay. I put one point on the domain. And then keep it as a data of the moduli space. And then if you have action, yeah, then certainly, yeah, yeah. Then actually, if you consider such a thing, then you have a translation symmetry. Put one map point, and then modeled by R is nothing but just forgetting this. And so, I'm more comfortable to put one point on the domain when we consider this. And when I consider this, actually domain has a certain fixed parameterization. That's what I want to say. So here, actually I have this L0, and here I have this phi of rho tau of H of L1, right? So if it is non-trivial deformation, then somehow this data somehow fixes this parameterization. I don't know how to say this. So domain is somehow always, domain is R cross 0, 1. No symmetry, because you have this condition breaks symmetry. But if this is constant, then yeah, you can recover the symmetry, but we don't want to do when we consider this chain map. So therefore I just put one more point on the domain, and but so maybe it may be too much, so there I just stop here. So anyways, identity gives the identity, at least on the cohomology. Yeah, so this one is there. So therefore, this is actually identity on this, and so on the cohomology identity. Yes. Maybe. Yeah. I don't. Yeah. So anyway, so this is a way. Okay. So now I have these things, and how we can see this. So maybe I cannot really tell you the whole story, but for this one, somehow the relation is somehow you have this phi and phi prime, and then at least from this phi and phi prime, you can cook up some homomorphism from here to here, which need not be this. And so actually, what we need is some Green theorem. In fact, Green theorem is necessary to show this. Yeah, what I erased here. So this one. So therefore, maybe it's too late to say this. So the Green theorem says the following. So if you have a pair of solutions, and then somehow you can cook up one parameter family of solutions which actually converge into this pair, right? Because this is one dimensional moduli space, and then this is an endpoint, and so it means that there is a path converging to this, right? So you have such a limit pair, and then from this limit pair, you want to cook up some solution in this space. So this is after you have a solution on cylinder, two cylinders, and then limit behavior, just asymptotic behavior coincide at these endpoints, and then you can glue them together to get a solution in these things. So in order to show this, actually we need two things. So look at the, I mean, it's actually splitting phenomena of trajectories from the sequence, and also Green theorem, right? So from here to here, you need glue, and from here to here, you just observe how it's split, right? And here we also do the same thing. So how they split, how they glue, and then somehow from phi and phi prime, we can get some chain map from here to here, which correspond to the composition of these two maps. That is actually coming from the Green theorem. And once you have this, then the story boils down to this. Because I have a map from here to here, and here to here, so therefore it just is this. So, okay. Once you have everything, then we are done. Because we have this phi h of t, and this phi h of t gives us something phi. And then we also have phi ht inverse somehow. Maybe I have to be a bit more careful. Yeah, this may be a bit more careful. Maybe here phi h1 or something. Maybe. From here we have this psi. And so like this. And then maybe what I'm saying is not so correct. No, sorry, this is not correct. Maybe it's better to write this way. So sorry, maybe phi of h of 1 minus t inverse. So what I'm saying is, here you have a group. So here you have identity, and here you have phi. And from here to here, we consider this phi of ht. This is a path. And now I want to consider the kind of inverse path. And the traveling. No. How to write it? Maybe I just draw it a bit different way. So phi ht bar or something. So this is the kind of inverse path. And so if you go here and then come back, and then this is contractible, so therefore in the end we just come down to this identity. So this psi and phi is actually homotopic to identity. And because they are chain homotopic, so therefore we have this psi composite phi star is equal to identity. But because this one, this phi psi and phi, and this one also this, but this one is phi psi by phi psi is equal to identity. And so therefore somehow this gives you, also you can do the opposite way. And so therefore you can get the chain map which induces inverse on cohomologity. Okay. So therefore, if you have this, maybe this kind of argument may be not precisely correct, but once you have these properties, and then actually you can show that they are actually they induce isomotion cohomology. Okay. So now I just want to say want to see this. So the argument is the following. So it's not so bad. So I have these two things, right? So J tau phi t h and J tilde tau and something. Okay. So now I consider one more parameter, and then I take a J S tau, and this is maybe also depending on t. And another one is this phi of h of tau t. No, S. Yeah, phi of h of s t, something like this. So this one, so S is in this region, and S equal to 1, J of 0 of tau is equal to J tau, and J of 1 of tau is equal to J prime, no, J tilde of tau. And H of S is equal to H. Yes. And sorry, H of 0 is H, and H1 is equal to H tilde, something like this. So I just consider one more family, one dimensional higher family, which actually connects these two things. And then we consider the following modular space. I don't know, maybe carry L, and maybe P tilde minus and P tilde plus. This is a union over S, and here you have S, and then you consider this modular space. Here I need to do this, right? So therefore maybe I need this JS tau and HS, something like this. Okay? So I have a family of almost complex structures, family of these Hamiltonian isotopies, maybe Hamilton functions, and then for each S, we can study this modular space, and then consider such a union. I mean, here is S, and then you have this union. And then now you look at the one-dimensional component, and then look at its boundary. And then what you get is that 4 types, maybe 3-4 types. And one is certainly, this is parameterized by the S between 0 and 1. So therefore, one boundary is actually, in this case, S equal to 0, right? So here you have S equal to 0 times this J 0 tau and H0. And then you have also S equal to 1 and this N of J1 tau and H1. But this one is exactly the same as this J tau on H, this side, right? So from this modular space, we can get this one of the chain homomorphism pi 1. And this one is this J tilde tau, and this is H tilde. So therefore, from here, actually what you get is phi of 2. So you have these two chain homomorphism from this modular space. Just count the number of modular spaces. And if it is only the components, then actually, if we put some sign, and then it is just the same. But in fact, we have more. So there are some sporadic moments, maybe SI, in 0 and 1, and then it may split. So like here I have this M of P tilde minus, and as I wrote somewhere, already I erased. So this Q tilde times N of Q tilde and P tilde plus, and here I have to take this J, S, I, tau, and H, S, I. Okay. So I have some finite many time, so that here we have a moduli space corresponding to this S and I, and this. Sorry, I need to put one more thing, like this. And then I have another term, so this is maybe Sj, and then here Sj, and then this N of P tilde minus, and R tilde, and H Sj tau, and J Sj tau, and H Sj times M of R tilde and P tilde plus. Okay. So yes. So yes. Something like this. Yes. Okay. So now I define chain homotopy. Chain homotopy is defined the following way. So we want to have chain homotopy like CF of this L1, L0 going to CF of phi of L1, L0, right? So here I have here P tilde minus, and then I want to I want to take a sum of the following. So I consider the following moduli space. So L of P tilde minus and P tilde plus of P tilde plus. So that this mu of P tilde plus is equal to mu of P tilde minus 1. Yeah? In the case of boundary operator, it is mu P tilde plus is mu P tilde minus plus 1. In the case of homomorphism, they are equal. Now we are considering chain homotopy, so therefore this is equal to minus 1. Right? So then this one, if you fix this data, then it is what expect dimension minus 1. So you may not have anything. But now we have one-dimensional family of them, right? So therefore, this one has expect dimension minus 1, but this one has one-dimensional freedom. So in total, actually this is zero-dimensional things. And then you count them in this sense. And then this gives you the chain homotopy. Because if you consider this term, so this term or this term, so they are actually exactly this one. So they are these Si and Sj are moment when this has solutions. So there are sporadic time when this is non-empty. Right? So if you count them, then actually from here, actually what you can, maybe I did not by kappa, and then what we can say is this phi 2 minus phi 1 if I put certain sign, and then this one is delta of L0, L1, L0 phi 1 composed with this kappa, maybe plus of kappa of delta of L0, L1. So therefore they are chain homotopy. Is it okay? So probably I am not so precise here, but my message is following. So you look at the moduli space, and then look at the boundary of the moduli space, and then from here you can read off certain algebraic structures. So here actually I have boundary operator just counting the cardinality of a modular space, and then you take a one-dimensional modular space and look at the boundary, and then this gives you delta square is equal to 0 sometimes. And for chain homomorphism, you have this one. If you look at the one-dimensional modular space and look at the boundary, and then you have this. And here, you look at this one-parameter family of such modular spaces. From here, you can get after chain homotopy. So everything that just occurs naturally, provided we have expected behavior of the modular space. Namely, no bubbling off of spheres or no bubbling off of disks, and then it is the case. And as I indicated in the morning, bubbling off a sphere is not really an issue. If you use certain abstract technique, and then certainly you can avoid it. But for disks, it is not. So therefore, when I talk about this, everything actually may be obstructed. So this kind of story works if you don't have disk bubbles. So this is actually what I wanted to say in this basic strategy of Floer theory. Still, I need to say something. So now I come to more easy story, and this part actually everybody must understand. And so what I said is the following. So no disk bubbles, no holomorphic disk bubble. Then maybe we get this, and also chain homomorphism. And chain homotopy, and so on. So that's a nice thing. And then if there is holomorphic disk bubble, then how this break down? And this is very easy example. So I maybe even just take a two torus here, or maybe if I work over the R2, maybe that makes it easier. So I take two Lagrangians. One is just this meridian things, and the other one is this circle like this. And then look at the definition of the Floer boundary operator. So I have two intersection points, maybe the picture like this. So maybe I have two intersection points like P and Q. And then you look at the holomorphic map. We want to have a holomorphic map from the cylinder, right, to here, so that maybe I just use some color. So maybe say this one is mapped to here, here, and this one is mapped to here, right? And then certainly you have kind of unique holomorphic map with this asymptotic behavior up to the symmetry of the domain, right? Because it's conformal mapping exists, and then it is unique up to automorphism. So therefore you have such a thing. But now you also have such a thing. So here I have another one here, you have another one here, and then look at this. And then here I have a yellow one, and I have red one here. And then you look at this red one and yellow one, and then you get maybe this one. And nothing else, right? Because of maximum principles, the mapping cannot go out. And also, I consider the index difference 1. I mean, I consider, isolated holomorphic strip. Then this one is unique up to automorphisms. So therefore, if I look at this, and then maybe you may say that delta P is equal to Q, and delta Q is equal to P, somehow. if we just follow this. And certainly, yeah, as I explained, we have to take certain covering space. So therefore, in fact, delta square p is not exactly p, but in different drift. But anyway, so you have this. So anyway, from here, you can say that this one is non-zero, right? So this one everybody understands. And why such a thing can happen? Just look at this example. So what I discussed is the moduli space of holomorphic strips from P to P, right? I consider the moduli space of strips from P to P, right? But more precisely, I may take a different drift, but anyway, so we want to consider such a thing, right? Of dimension 2, relative dimension 1. So mu of P tilde tilde minus mu of P tilde is equal to 2. So what happens, right? So the picture is the following. So I have this cylinder, and then I have this picture, and then I start from P to P. So I have P here, I have Q here. And then I consider the following curve, following map. So this boundary is sent to a boundary like this. Like this. And this boundary is mapped to this. We have such a holomorphic mapping unique up to automorphism of the domain, right? Because I just make a slit here, and then this part is conformally equivalent to this one. So therefore, we have some conformant there. And so we have this. And so therefore, apparently it has a one-dimensional freedom. So this point can be anywhere. So therefore, it can just reach to the Q, or maybe just shrink to point P. So there are two extremals. So one is, so this one actually split into two things. Just going here, and then coming back like this. But then this yellow one is also going this way, and going back this way, right? So therefore, this is the picture exactly happening like this. This picture. But the other one is, so red one is just here, and the yellow one just go around once. And how to understand this? In this case, this one is actually like this. So I have a cylinder. So this one actually like this, going to this, right? And this, right? So just split into two parts. And the other one is in fact the following. So I have a yellow one, so therefore, in fact, I have something like this. I have something like this. But this is constant. So all cylinder and all strip actually map to this point. And then I can get some if you rescale the mapping near the boundary point, and then actually in the end we get certain holomorphic disk here. So we have this thing, right? Appearing this way. So therefore, it is not really this, right? So this limit looks like this. but we have other limit, which I cannot draw in this picture, is in fact in this case this. So this one is not the splitting into the trajectories. So therefore, we cannot really conclude this one is equal to 0. Okay? So this is the reason why delta square is not necessarily 0. So therefore, Floer theory may not be defined. But then what we have to do is the following. So then the bad thing is a holomorphic disk. And then if we still want to rectify the boundary operator to define Floer theory, then certainly you have to consider all the holomorphic disks somehow systematically to understand what kind of bubbling happens there and so on. So then we need some algebra to control it. So that is our filtered infinity algebra. But before that, maybe I also give you some example, and that must be, I can speak in maybe 5 minutes. So next one, maybe I can see. I think that you can really understand. So this is a very easy example. Two sphere. I have two sphere. Then I consider two circles on it. So like a small circle or a great circle. So I take circle here and here. Okay. So I have circle C1 and circle C2. Okay. And then if C1 and C2 are small circles, so small, they are small circles, then maybe either C1 or C2 is enough. But then actually there is a Hamiltonian diffeomorphism or area preserving diffeomorphism, so that this C1, C2 are disjoint, right? Maybe one of them is enough, right? Okay. So let's suppose that C1 is just a small circle. Then you can just rotate the circles, and then you can easily displace. You can just put it in a position away from this thing, right? So therefore, if all the argument works, then certainly the Floer theory, Floer cohomology must be trivial in this case. And if C1, C2 are both great circles, then in fact you cannot displace them, right? Because simply area reason, you cannot displace them. So therefore, there is no such things, no such phi, right? And in fact, in this case, we can define Floer theory so that Floer theory is non-trivial. So I want to discuss it a bit more. So at the beginning, maybe we may just write boundary of P is Q or boundary Q of P. And this way, probably it doesn't really give the difference, right? Because in this case, in this case, if it is P and this is Q, if you just count them, and then it doesn't matter which size of sphere you take, right? Because so I have here, maybe I have one of them is a great circle, both of them are great circle, or both are small circles. Maybe we can also put two small circles in such a position, and then there is one-to-one correspondence of these holomorphic strips. So therefore, you can get a one-to-one correspondence of the moduli space, right? So therefore, something necessary to do this. And then that is somehow a thing related to this taking these covering things. So more simplicity, actually we can do the following. So I said this delta of P is go to something, right? I wrote this P and Q. And then I want to put some Q here. So this is just a number, but maybe I also encode the area of the class. So maybe I just put some formal variable T. This is just a formal variable. And then I may put this some area of the holomorphic strip. So here, for instance, in this case, here I have, say, A here, or here B here, C here, or D here. And if I just put in this way, what happens with this? So in this case, delta of P, I think I just look at this. So from this way, so maybe this C, dC of Q. Maybe I need to some sign, but anyway. And then another one is so you have wait. So I have to remember how to do this. So I have this one is red, and this one is yellow, right? Then I have to look at wait. Red and yellow, right? So red and yellow. So I can do this, and then another. Sorry. This one is TB. Sorry. Yeah, it depends how you name them, but anyway, so then T of D of Q. Okay. So this side and this side, right? And then delta of Q is equal to plus minus T of A Q plus minus T of C of Q. In fact, we can put some sign so that this one is in fact maybe something like this. Maybe something like this. And so therefore, if you take this delta square of P, then this is after TA minus TC and TB minus TD of P. I think so. And if I think my picture is not so nice, but somehow if I have this, disk, I have this disk, right? I have this disk. Is rotated to another one. This one. Then what we have is area is A plus B is equal to B plus C. So from here, I say that A equal to C. In such a case, actually, this actually cancel and just get delta square equal to 0. In this case, actually, that's right. For instance, so if I have two circles, so that they are Hamiltonian diffeomorphic, they are Hamiltonian isotopic. In other words, there is a family of area preserving map sending this circle to another circle. In such a case, actually this one is equal to 0. But otherwise, this one is non-zero, right? So what we can see is the following. So if C1, C2 are Hamiltonian isotopic, then this delta square is equal to 0. And if not, then this one is not 0. So in this case, we don't have a Floer theory, Floer cohomology. Yeah, we have some field at infinite level, but not so this one. But if C1, C2 are Hamiltonian isotopic, but not great circle, then this Floer homology of this C1, C2 is equal to 0. So why is the case? Because in such a case, actually now A and C are equal, so therefore this one is 0. But in such a case, actually B and D are not equal. So therefore, even though Q is killed by boundary operator, Q is hit by some constant times P. So therefore, the cohomology vanishes. And if C1, C2 are Hamiltonianized, both are great circles. So both are great circles, and then they are Hamiltonian isotopic. And in that case, actually, A equal to C and also B equal to D. So both differential vanishes. So therefore, in this case, Floer homology of C1, C2 is equal to this cohomology of the circle. Okay. So maybe you may just follow the definition of the boundary operator and then look at these strips and then put some weight in the definition of the boundary operator, and then you can just have this. So in this example, you can see that in general, delta square is non-zero. And if they're Hamiltonian isotopic, then we can define Floer homology. But sometimes it is 0, sometimes non-zero. So that's the first part of this. Okay. PAP. Where? Second line. Ah, sorry. This is P. This is P. Okay. Something like this. Okay. Okay. I hope this part is okay. At least up to homotopy, right? But I don't know whether it's commute strict.
When it's a phenomenon,
I think this may be already finite dimension. But so you probably use some finite dimension topology to do this, or so.
Yeah. Because I don't see. What
I wrote is this equation. Right? Sorry, that one. Okay. So what I okay. Yes. Sorry. So so this one going to this CF of phi of A1 going to CF of psi. right? So here I have this, maybe in this Hamilton first page, and then here okay, and then maybe I use this. So this is much easier things.
So this is H.
No, it's actually much easier things. Maybe I can just compute. So okay, you have 20, and then I map it by 5 raised to t, and then I multiply the k of t, right? And then I just take a derivative of this.
So this one I think it's
So this one is equal to x of k over t over phi of k of t over phi of h of t over t plus phi k t star of x of h of t of phi of h of t. Yes, there is such a formula.
Yeah. So I mean, what I mean is that H and K precisely all of this.
Yeah. But this one is actually this one. I forgot something coming from H.
It is also the kind of T.
I forgot maybe something like this. I don't know, maybe inverse or something. I forgot.
Oh, okay. Yeah, that's fine.
Something like this. So there is some
I think it's equivalent.
Yes. But in that case, actually, x and y are time independent.
So
Here actually time dependent. Time dependent. So can be right half of case actually it is time independent. So somehow I forgot this one is. But it's much easier. Just compute this, and then look at this thing. So this is the Hamiltonian k, and then you look at this, and then somehow we can think of it as a function vector period. Yes. So what I said is somehow you have these two things, right? And then in order to define this, I need to use this moduli space. And from this t tilde minus to maybe q tilde, and then that is for this. And then from here to here, I have to use this n of q tilde and I don't know, maybe p tilde plus or something. Yeah, I mean, maybe just the simplicity I can enter the rate, and this is my rate, and then this phi of h of t tilde minus is the sum of this cardinality of this thing p tilde minus and q tilde and q tilde. Maybe I just write it later, but then this phi of k of q tilde is the sum of this thing. So this is yes. And then from here, after we want to consider someone from here to here. And so this is somehow related by k composed by h. And that is actually this one. If you compose them, it's p tilde minus, and then it's a sum. Because first you apply this, and then you have this np tilde minus and q tilde, and then this. And then like this. So therefore, if we know that what is the cardinality of this one, so this is zero dimension, this is zero dimension. And now we consider function n. And here I have to take a little bit different, but somehow in the negative part, maybe it is. So, yeah, maybe, yeah, we have two ways to write it. But we just consider this equation, but u of r plus 0 is always 0, but u of r of 1 is in this phi of h of rota of L1, something like this. So this one. So I have L0 here and L1 here, but L1 actually deformed by this phi. So this is phi of h of rota of this L1, right? So we have this equation. And then we have another equation, dv now plus dv dt is equal to 0. And also boundary condition, this one is same. So v of r equals to 0 is inside 0, but v of r of t is not contained in this phi of k of another row, but maybe same maybe without. And then just take it to phi of the 1. So again, yeah, I can deform this. So here, this is L0, and this is L0, and this is actually phi of L1, and here actually this is phi of h of rho of L1, right? So like this. And then I have another solution from here to here. So this is L0, and this is phi of L1, and this is psi of phi of L1. And then here I have this phi of k of rho tau of phi of 1. So this is a tau. So this is a tau. This is a tau. And then we want to glue these solutions together. So somehow, yeah, then actually we get certain. Yeah, I think you can put them together. And so therefore, there is something related to the composition of this. But this one is another mass coming from here to here directly. But we have these two maps, and then
so you need to have another one.
Yeah. Yeah, so you have these two things, and then we try to, yeah. But there is some way to do this. Well, you can just concatenate these two things.
Yeah, but all this applies also to common foundation.
Yes.
Maybe the standards already like common foundation.
Yes, that's right. But maybe people didn't study such a thing before Floer. And if you look at the book by Matthias Floer, actually he has a most homology book. And that is actually, the finite domain version. Basically. But in his case, actually, he can prove some axioms, like Eilenberg scheme axiom for most theory. And so he didn't really compute it. So anyway, maybe I can tell you later. Maybe some water, yes. Well, maybe tea or yeah. So I don't know. Maybe today maybe I say it. Yeah. is just the index problem, right? So, okay, this one. Okay. No, up to here it's okay. So, okay, from here, this is over. And this is over, this is over. And this is okay.
Can I just add in?
Yes. Thank you. And then I just calculate double this. Okay. Okay. So maybe I just briefly mention this grading things, like index and so on, and then a bit about orientation, namely the sign issues. And so here I consider the following thing. So I have a Maslov index. So last time I said the following. So you have sigma, and then you take a boundary of sigma, and then maybe it's a compact surface, maybe a compact oriented surface. And over here, you consider some pair of vector bundles, namely E is a symplectic vector bundle, and F is a Lagrangian subbundle. I mean, the fibers are Lagrangian subspaces in the symplectic vector space. And then from here, maybe I define this mu of this thing, right? Mu of this EF and sigma d sigma or something. But this one, yeah, is a kind of topological index of a certain Cauchy-Riemann operator, related to the Cauchy-Riemann operator. So maybe I start speaking this. So firstly, I consider sigma is just a Riemann surface, maybe closed Riemann surface, so compact without boundary. And then let E be a complex vector bundle, but maybe I take a holomorphic vector bundle. And then we have a d-bar operator. So it's actually a map from omega 0, 0. So this is a complex manifold, so therefore complexified tangent space decomposes 1, 0 and 0, 1, and then cotangent bundle also decomposes into this. And then here I have this sigma and E going to omega 0, 1 over sigma and E. And then this index of this maybe complex index of this operator, maybe I denote, I just put E here, is given by the following formula. So this is so-called Riemann-Roch theorem, but maybe in higher dimension, maybe people call it Riemann-Roch theorem. So this is the Chern character of E, and cut product with third class of this sigma, and then evaluate with this sigma, right? But for Riemann surface, certainly we have only 0 or 2, the cohomology in 0, 1, 2 degrees, and they all even degrees. So therefore, in that case, actually it is only 1 plus C1 of E here. And this one is the, wait a minute, this one is, what? So, sorry, this is not correct. This is rank, sorry, rank of E here. And then here, total is maybe just 1 plus C1 of T star sigma or something like this. Is it correct? Okay. So, I think so. So therefore, in this case, actually I have only these two things. So this one is equal to rank of E times this thing. But this one is equal to 2 minus, oh sorry, maybe I have to multiply 2. So 1 minus G, 1 minus genus, and then I have another one is C1 of E. Yes, like this. So this is, because this is one dimension, then this is just like this. And so, yes. So now, yeah, I just consider the case of P1, say, and then it's much here. So, because I only use disk data, so in this case, actually the index of complex index of this guy is equal to just rank of E, complex rank of E, plus the first term plus this. Like this, right? And okay, so this formula somehow I used in the morning talk because I gave the dimension the modular space of holomorphic rational curve, and then somehow it comes from this. So this one is okay. But now I consider the kind of relative version. So I have here disk, and over here you have some boundary E here, like that. And then over the boundary, I have this F, right? So now I consider this as a holomorphic bundle. Maybe just a trivial bundle is okay, but maybe just a holomorphic vector bundle, like a complex vector bundle. And this one is so-called total real bundle. Okay. So namely, if you take a complex equation of F inside of E, and then this one is actually like this, right? So this is, well, maybe we may also say that maybe F and square root minus of F is equal to A, like this, okay? And then we can consider the following, so omega 0, 0 of disk and boundary going to E, F. So this is a section of boundary E, so that on the boundary, the section lies in this total real bundle. And then you may consider this omega 01 of this disk and E. Maybe, yeah, in this case, actually, maybe I may take, say, certain completion, like a Sobolev space completion. Then maybe here I may take a W12 space of this, and here maybe L2 space of this. And then we consider such operator, like a D bar of here. And then, in this case, actually index formula. But in this case, operator is not complex linear because this domain is not complex vector space in usual sense, because if you multiply square root minus 1, and then the boundary value doesn't really lie on f, right? Because f is totally real. So therefore, we can only consider this in real index. And this one is equal to the rank of f plus the Maslow's index of these things. So, yeah, I have here two things. So, I don't know. Here. So this is actually a complex rank, right? And this is a real rank. And complex rank of E is, yeah, in this case, this one you can think of it as a rank of, complex rank of E, right? And so now I have a disk here. Over here, I have this vector boundary E, right? Holomorphic boundary E. But over the disk, maybe we can just trivialize it to disk times, say, CK or something. And over the boundary, I have F, right? F is over the boundary. We have this. And then I do the following. So I have two copies of D, and then glue them along the boundary. I just glue them along the boundary. But here I take usual complex structure like J or maybe square root minus 1. But here I put a square root minus of square root minus 1. So it's opposite orientation. And then, so this one and this one has opposite orientation, and then glue them along the boundary. And certainly, this is a picture like this. So you have here, you have a disk, and then this actually reflects, you have a certain reflection along this equator. So it is actually the anti-holomorphic involution here. And over here, you have this E, this bundle here, and then maybe also I put E here. So I have a bundle, complex vector bundle, but here I just regard them just a real vector bundle. And then somehow here I put complex structure like this, and then here I put complex structure like this. So just take the conjugate ones, and then want to glue them together by the following formula. So now you take here E of square root minus 1 of theta. So over the fiber there, so I have D2, and then here I have a square root minus 1 of theta here. And then actually I have a copy of this, so therefore I have the same disk like this. And over here I have a D2 cross CK, and here I have a D2, sorry, CK is not good, so I don't know, maybe CK is okay, but okay, so D2 cross CK. But I put the opposite complex structure here, and then want to identify this. So here I have E square root minus 1 of theta, and here I take Z, and then I just map it to E square root minus 1 theta, and then R of theta of Z. And what is R theta? R theta is a map from CK to CK, which is a reflection along this fiber. So this is a reflection along this f over ei theta, e square root minus 1 theta. Does it make sense? So what I'm doing is this kind of Schwartz reflection principle story. So here you have complex things, and then here it is actually something conjugate to that, complex conjugate to that one. But then what kind of complex conjugation do you think? So this complex conjugation is actually just along this total real subspace. So in this way, actually what you get is CP1. And here you get some boundary E here, right? And then this one can be understood the following way. So because here we have this sigma. So here I have this omega 0, 0 and CP1 of this E. And then here I have omega 0, 1 of CP1 of E. Right? And here is the involution, some sort of involution, sigma tilde maybe. So on the base space, sigma is this anti-holomorphic involution along this equator, right? In the fiber, actually, I do this kind of complex conjugation in the fiber directions. It's a complex conjugate one. And also here, because on the fiber boundary E, I have such a involution, complex conjugate linear involution, and then the base space on the tangent boundaries, cotangent boundary, we also have this. So therefore, we also have this thing. And then we can decompose these two spaces into the eigenspaces of these things. And then actually we have two, because they are involutions. So therefore, we can have the decomposition like this, right? So this one is decomposed into omega 0, 0, CP1 and E, so that this sigma tilde is equal to identity, and omega 0, 0 of CP1 and E and sigma tilde is equal to minus identity. And then it is mapped to this thing, right? So roughly speaking, we have this sort of decomposition. Right? It's kind of Schwartz reflection story. And these two spaces are related by the multiplication by square root minus 1. So therefore, you take the index of this guy, and then because they related by square root, multiplication by square root minus 1, so the index of this one and the index of this one are the same. And this part can be understood as this part. Yeah? Because if sigma t is equal to 1, then the section is fixed by this involution. Then on the boundary, it takes values in the subboundary f. So that is nothing but this condition. So therefore, what we can say is that index of this EF of this D bar operator in this case, and this index of this operator D bar on E, they are the same, but here this is a complex index. And this is a real index, right? This is a real index. Because here we only have the real index. And so certainly, as I said, this one is equal to this one. This is a complex rank is equal to real rank, certainly. And this one is also equal to this one. We can directly prove this, but is equal to this mu of this EF. Okay. So as an integer. Okay. So sometimes I want to have this picture because people may not so familiar with these boundary value problems and may wonder whether it is Fredholm or not and so on. But actually this on two-dimensional, I mean on the Riemann surface, and this Lagrangian boundary condition really gives you Fredholm operator. And somehow, because such a thing is actually, you can see in this closed story, and so somehow you can guess that this is the case. Okay. So now I want to speak a little bit about the index of the linearized operator. Okay? So I have U in this M tilde of P tilde minus and P tilde plus. So it's a solution of certain cosine operator, like a du d tau plus ju of du dt is equal to 0, right? So maybe we can just write it as an equation like d bar of j of u or something. Maybe people usually think of it as one form, so therefore I need to put some form part here, but I can trivialize it in this case, so therefore like this. And then what is the linearization operator of this? Right? What is the linearization operator of this? So maybe this C is a section of this, right? Sorry, not a disk. Sorry, not a disk. Like this. So I have a map U, and then this is a maybe solution of this equation. But then I just perturb this map, without assuming this kind of equation. Then I have a vector field along this map, preserving boundary conditions. So therefore, the boundary has to be mapped to this boundary things. Okay, so this is a kind of infinitesimal deformation of this mapping U. And so what is this, right? So it may not be so precise, but you can just get some rough idea from here. So you have map U and want to deform this map in the direction of C. So therefore, in local coordinate, maybe you just consider this sort of thing, right? In local coordinate, you may do this. And then just consider this equation. So just consider this equation, and then just take the limit, take the derivative at epsilon equal to 0. Then what is this? From the first term, certainly we get this dxi d tau, and from the second term, maybe we have this delta of j of xi and du dt terms. And then if I differentiate the next term, and then this is something like this. So roughly, you may get this kind of computation. And then if you look at this and this is a Cauchy-Riemann equation. And now, in general, we may have this sort of term, but somehow, if EU is finite, and then it actually converging to an intersection point, it's, maybe I don't need to say this today, but, and so therefore somehow this term is getting smaller and smaller as tau going to infinity, right? So this is the equation over this cylinder, and this one is very small at infinity, right? Not so much contributions. And so this one may be active in certain compact portion. But anyway, you can think of it as kind of compact perturbation of this operator. So if you know that this one is Fredholm, and then this one is also Fredholm, and the index doesn't change if you drop this. Okay, so therefore, I just roughly consider the equation like this. So this one is equal to dxi d tau plus j of u of dxi dt plus something else. We shouldn't really forget this for some purpose, like when you want to show that this operator is really surjective or not, and then it depends on the operator whether the operator is surjective or not. So therefore, you cannot really, in general, you can really drop this. But for index problem, certainly you can just drop this. Okay. So now I consider the following picture. So this is a cylinder, and then I have one family of Lagrangian submanifold, but if this else, I have Cn. So Cn, I take some unitary structure. So here I have this J naught, J standard. It's a complex structure, and also we have the unitary structure. Hermitian metric, and then from here, actually we get this omega standard. So we can think of it as a simple vector space. And so now, if you think of it as a simplex vector space, here you have a notion of Lagrangian submanifold. No, Lagrangian subspace, just linear subspace on which omega 0 vanishes, and dimension is just half of this. So half-dimensional linear subspace on which omega 0 just 0. And such a thing is certain total real things. So this one is actually total real. And if you consider the Lagrangian subspaces in this simple vector space, you get so-called Lagrangian Grassmannian. And here you can also consider half-dimensional total real subspaces, and then you get such a Grassmannian. And then they actually, I think they are homotopy equivalent, so therefore, for homotopy problems, certainly you can work on either side. Okay, so therefore, if you have Lagrangian, you have a total real things, and if once you have total real, and then as I mentioned there, it is actually a Fredholm problem for the compact manifold. And in our situation, the situation may be a little bit different, but maybe I just try to think of it. So here I consider a family of Lagrange subspaces. Okay, so here I may consider maybe lambda 0 of tau. It's a family of Lagrange subspace here, and here maybe a lambda 1 of tau here. Just to consider family of Lagrange subspaces, so that this lambda 0 of tau is equal to maybe lambda minus infinity of 0 for tau sufficiently small, and this is equal to lambda 0 infinity for tau sufficiently large. I just consider such a path. And here I have this lambda 1 of tau, the same thing, is lambda 1 of minus infinity as tau, so negative. And here lambda 1 tau is equal to lambda 1 plus infinity for tau so large. So I have such a path. And let's suppose that they are transversal. So this lambda 1 minus infinity is transversal to lambda 0 minus infinity. And this lambda 1 plus infinity is transversal to lambda 0 plus infinity. So I just assume this such a thing. Okay. And then here, I consider the index problem. So namely, I have a d bar operator on this omega, maybe omega 0, 0 of this cylinder and R cross I, and then it is mapped to this CK, the complete vector space, and then they are mapped to these things. So I don't know how to write it. Maybe lambda I and tau. So this is a boundary condition for this. Then I just mapped it omega 01 of R cross 01 and CK. And yeah, maybe W1 to completion or something. Okay. And maybe, we can also study this problem, but without loss of generality, maybe we can just keep one of them constant. So let's suppose that this lambda 0 tau is just one thing, lambda 0. So assume that one of them is just constant, and just the other side is moving. And then how can you understand this problem? Okay. So maybe the general case may be a little bit complicated, so therefore I just do some computation for very easy case, and then just reduce a general case to that case. Okay. The thing is something like this. So I have this, and here I just consider the bundle over here is just R cross 01 times just a complex plane. And here on the lower boundary, I just put R here. And on the top, I put E to the square root minus 1 of, say, I don't know, anything is okay, but maybe FGH, maybe, I don't know, maybe rho maybe miss. Yeah, okay, F of tau, yes, of this, okay? So I just consider real subspace in the complex plane, and then I just rotate it by multiplying this. And then here, we have to assume that this F tau, maybe F infinity, is not, this one is not equal to plus minus 1. Right? So then this one is not in the multiple of pi, right? Then it is transversal to this, right? Okay. So we consider such a problem. But this problem, maybe you may try to compute the index directly. But I just suggest the following. So, okay, so now I consider psi tau t. So this is just in general, just a complex number. But psi of 0 of t, so psi of tau of 0 is a real number, okay? And psi of tau 1 is in this e to the root minus 1 ft, f tau of r, right? You have this. And then this is actually moving boundary condition. And in the nonlinear story, I also consider something like this. And then I using Hamiltonian to move one of the moving Lagrangian to a fixed Lagrangian. And here, maybe we can also do the same thing. So namely, let theta tau t is just equal to this e to the minus square root minus 1 of f tau of psi of tau t. Then this thing now has the following thing. So psi of tau of 0 is certainly, sorry. I forgot to put t here. So I have to put t here. T is in 0, 1 of this psi of tau t. So t equal to 0, and then this one is just 1. So this is psi of tau t, but psi of tau 0, but psi of tau 0 is real, right? Like this. And then how about this theta tau 1? In this case, I just multiply 1 here, so therefore they cancel out. So this one is also staying inside of this thing, right? So now I can convert this boundary value problem to just a boundary problem for this. And then just write down the equation. So for psi, I consider equation like psi goes to, say, d psi d tau plus square root minus 1 of d psi dt. And how about theta here? And then actually I have to compute, but plus something. So just I want to show the computation here. Then you can see how things changes. So theta is that one. So therefore, if I do this d theta d tau, and then I have to differentiate that one. So therefore, I have minus square root minus 1 and f prime tau and t, and e to the minus square root minus 1 f tau t of psi of tau t. So this is okay. And then second term is just a difference in psi. So then this is just like this. Okay. And how about this? Now I also have the same thing, but here I have a bit different effect. And e to the minus square root minus 1 of f tau t of psi tau t plus e to the minus square root minus 1 of f tau t of d psi dt. So this term and this term look similar, but difference is that this one is the function f, and this one is derivative function f. Certainly. And if I assume this condition, then this Lagrangian is fixed for tau sufficient small or tau sufficient large. So therefore, this derivative actually vanishes at tau near the infinity. So therefore, this one is actually compactly supported function. This is a compactly supported function. But this one is not. This one is not. So if I do this d theta d tau plus square root minus 1 of d theta dt, and then this one is equal to, maybe this is not enough, but okay. So this one is e to the minus square root minus 1 of f tau of t of d psi d tau plus square root minus 1 of d psi dt, and then we have different terms. So here, this is actually multiplication is plus. So therefore here you have f tau, and this is here, and then psi. And then finally, I have sorry. I should delete it. So I want to consider this thing. So how I can write it? Okay. So sorry. So this term is from here. It's okay. And this term is from here. So therefore, yeah, if I compute this, and then this is equal to this. Yes. And then I have to add this, right? So I have to add it. And theta. Okay, so this is theta, like this. And then another one is, so I have to add it. So therefore this one is plus f tau of theta. Okay. Sorry. I should start from here and then compute this. This is minus. Because I move it to the other side. Maybe this is minus, yes. Yeah, so anyway, so I do this sort of computation. And then, so originally I consider this operator. And what the operator corresponds to this. And this operator is exactly this. So this operator is this one. So square root minus 1. And f prime of tau, and t, and theta, and finally, maybe I made a mistake in computation, but f tau of theta, something like this. Yeah, okay. And as I said, so this part is a compactly supported function. Compactly supported smooth function. And so therefore, yeah, if you multiply theta if we multiply this compact supported smooth function to theta, it is actually a compact perturbation term for this operator, because we are considering a map from, say, W12 or W1P to L2, LP, say, and then well, maybe 2, and then anyway, so this multiplication by this function is compactly supported. So therefore, in the compact portion, then this one is included here is a compact embedding, right? By Redlich-Kondratev theorem. So therefore, this part doesn't really contribute to the index problem. So for the index problem, you just drop this. So just for index computation, we can drop several things. But this one is certainly we cannot drop because it is not compactly supported, and this is a really important part of the story. Okay. Then I want to consider kind of Fourier expansion of this function. So for each tau, we may want to decompose into a sum like an tau of e to the square root minus 1 of n t. Maybe here I may write t here. Okay. And this is actually a real function, real valued function. Is it okay? So t equal to 0, this is 1. So therefore, yeah, boundary value real, so therefore it is real. And t equal to 1, then this term is either plus or minus 1. So therefore, this is again real. So therefore here, so therefore, this boundary condition now come to this condition, right? So I have a bunch of real value functions and then try to see something. Okay. And now you look at this operator like, right? But if you consider this, then certainly sorry, in pi must be somewhere. Sorry, n pi t, right? N pi t. Pi must be somewhere. Where is pi? Okay, but anyway, here must be pi t. And so here I have to n pi t. So therefore, this is minus n pi, yes, of e to the square root minus 1 of n pi t, right? So therefore, the spectrum of this guy is this one, right? So it's just n pi, and n is just 8. Okay? But here, I have a kind of constant term. I mean, just multiplying this one to theta. So here I consider the operator like minus 1 of d dt plus this, minus of f tau. Minus of f tau. So this kind of family of operators. And this is also real value function, right? Because I just put this phase of this. So therefore, this is real value function. So therefore, it is actually a self-adjoint operator. And what is the spectrum of this? So spectrum, we can compute it in exactly by this, and this is just like this. So therefore, this is actually n pi minus f tau, right? For each tau. So as tau changes, the spectrum changes this way. Okay? So I have a family of operators, and then look at, for each tau, I look at this self-adjoint operator, and then just compute the spectrum of this. And then there is a notion of spectral flow, and the index of this problem is actually equal to the spectral flow. Okay. So maybe now I can just tell the following. So now I consider a function maybe from R to some Hilbert space. In this case, actually, maybe I take L2 space or something. No. Yeah, W12 space. But I mean, just for simplicity, I consider the Hilbert space. And then here we have a family of self-adjoint operator. And then consider the problem related to this, right? So namely, the problem is if we have psi, and then just solve this equation, for instance. And then in this situation, so very special type of self-adjoint operator. So namely, H has an orthonormal basis like EI, complete orthonormal basis here, and then I may just consider A tau of EI is equal to this, I don't know, maybe lambda I of tau of EI. So it's a very special type of operator. So eigen vector doesn't change according to tau. So here actually I consider this function. This one doesn't depend on tau, right? So I just take the same vector, and then this operator has a eigenspace decomposition like this. So therefore, just consider these things. Very special type of self-adjoint operator, and then try to see this. And then we can just do the same thing. So psi tau is equal to sum of ai of tau and ei. And then just plug in this equation, this one to this one, and then what we'll have is just d tau of this ai tau plus lambda I of tau is equal to 0 for any I. Yeah. So this is a equation like this. And then this is just ordinary differential equation. So therefore you can solve it, right? And if tau is sufficiently negative, then this lambda I is just constant, maybe lambda I of minus. And then in this case, this ai prime is equal to minus of lambda I minus of ai. So therefore ai is equal to the constant times the exponential of minus lambda I tau or something, right? Yes. So you differentiate with this tau, and then this one come up. So therefore, like this. So if tau is so negative, then if lambda I is positive, then it decay, right? So it is positive, then decay as tau goes to minus infinity. But if it is negative, then tau is negative. Sorry. What? Maybe I made a mistake. So it is positive, then this is negative. Sorry, it is opposite. If it is negative, then it decay. But if it is positive, then it actually grows exponentially as tau goes to minus infinity. And opposite thing is true for this. So lambda I plus here. And if this one is negative, and then it decay. But if this one is positive, then it grows exponentially, right? As tau goes to plus infinity. Okay. So if you have this equation, and then try to see certain solution which satisfies certain decay condition, and then the only case we have such a solution is the following. So for this lambda I must be negative for sufficient negative tau, and wait. It must be opposite. Maybe this is opposite. This is opposite. And then this must be positive at positive infinity. Namely, if you have an eigenvalue which is negative at infinity and positive at positive infinity, and then it contributes to certain solution. But if you don't have such a property, and then this solution must blow up either at positive infinity or negative infinity. So we are talking about, we are thinking certain problem here, then we have certain LP boundedness or L2 boundedness. So therefore, we cannot have such exponential growth function, right? So only we can allow these things. So therefore, the solution space is just following things. So you just look at the solution, you just look at the eigenvalues, lambda I tau, so that how this the function lambda I close 0, right? So if it is from negative to positive, it will contribute solution, but otherwise it is not. So this is one. And then if you consider the co-kernel of this, and then somehow you consider the adjoint, adjoint operator of that, and then the situation is somehow getting negative, getting opposite. So therefore, for the co-kernel, actually, operator is different, and yeah, because operator is different, because this is self-adjoint operator, but this is not, right? This adjoint of this is minus of negative of dd tau. So therefore, this part actually changes the sign. So therefore, this behavior changes. So therefore, we can say the following. So the index of this dd tau plus a tau things is equal to the number of I, so that it is lambda is negative, but lambda I is positive, minus I, so that lambda I is positive and lambda I is negative. Okay, so this is so-called spectral flow of the family of one-parameter family of self-adjoint operators. So this is a so-called spectral flow. So in my case, actually, I assume that they are transversal at here and here. So therefore, this one is not in this pi z. So therefore, the operator here has no zero eigenvalue at infinity. So therefore, this is actually non-degenerate at these both sides. And so therefore, it is actually a good situation we can talk about spectral flow. Okay. So now in this situation, I mean, I may get this minus sign that somehow I don't know if this is true or not. But anyway, so this, right? So for each n pi, we know how spectrum changes, right? So I have some f tau. I have some f tau here like this. Then we just consider the shift, right, by this. And so this is positive?
I said that's plus.
This is plus? Okay. Okay, maybe plus. Sorry, I'm not so good at this. And so then just compute this number, and then in that way actually you can compute this index. And finally, yeah, so we have to compare it with this. So sorry. So we have this Diva operator on with this property, right? So sorry. We have this operator Diva with this property, so omega 0, and then boundary value condition is just one is R, and the other one is e to the root minus 1 of f tau of R to omega 0, 1 of C, right? I mean, C is just the values. And then this one is equal to the spectral flow of this family, this square root minus 1 of ddt, square root of ddt, square root of ddt plus f tau. Okay. So this is okay. And finally, I have to really see how it is. So, so let's consider the case that f tau is something like this, right? So f tau maybe start from negative, but not yet pi. So this is minus pi, but maybe start somewhere here, and then end up with this, like this. This may be m pi. So I just look at the difference of values. So maybe that's better. So I take f of plus infinity minus f of minus infinity. Okay, sorry. I think this one is not good enough. This one is not good enough. Sorry. This one is not good enough. So I don't know how to really say this. Sorry. This I computed some time, but this is not really the case. Sorry. So if I start from here and then end up with this, so if this is this f of minus infinity and this is f of plus infinity, and then it crosses eigenvalue m plus 1 times. So therefore, in such a case, actually this spectral flow is m plus 1, right? Yeah. So I don't know. This one is plus or minus. So that somehow I think a little strange. Sorry, maybe I made a mistake in some computation, but yeah. So sorry. I made some mistake in computations. So sorry. So yeah, I think my computation is not really correct. Somewhere I did. Yes, I did some computation, and then in my computation, actually I have a negative sign of this. So yeah, negative sign of this for some reason. I don't know. What I wrote here is actually negative spectral flow. That is actually, I think, I don't know. Yes. Anyway, this is the way. So finally, I just check it with some other examples and then just tell you how they are related. Okay. Yeah, I think I did some computation, but not really so fast. Okay. Sorry. This. Yes. Maybe I made some mistake in my computation. Okay. But anyway, so this is analytic index story. So analytic index is just a dimension kernel, one dimension co-kernel, and that can be written in spectral flow terms. And then so this is up to now it is analytic index, and we also have a topological index. So this is another thing. So I have, say, Lagrangian Grassmannian of this R to n and omega naught. And here, I consider the path lambda t, so that this is actually transversal to this. So lambda 0 is transversal to this fixed Rn, and lambda 1 is also fixed Rn. So they are actually fixed Lagrangians. And then I want to give you the definition for topological index in this case. So the definition is the following. So here you consider all possible Lagrangians, but now we can also consider Lagrangians which are not transversal to this fixed Lagrangian. So maybe I denote by sigma, and then this is just fixed Rn. So this is actually a subspace so that this one is not transversal to this Rn. And this is so-called Maslov cycle. And codimension 1 cycle. And I want to explain how it is. Or maybe this is a quite singular object. I mean, it has some singularities, but still give us the codimension 1 cycle in Lagrangian Grassmannian. So, in fact, what we can show is that this complement is actually isomorphic or diffeomorphic to the following Euclidean space. So how can we see this? Okay. So I fixed. I fix one Lagrangian, anything. So here I fix Rn, so therefore I fix Rn here. And then I have another Lagrangian subspace, L0, so maybe better to denote it by different letter. So maybe this one I may denote it by, say, lambda 0 here. Okay, lambda 0, upper 0. And then take pick L0 so that pick L0 so that L0 is transversal to this lambda 0. Okay, so this is the transversal. We can always find such a thing. And if you pick such a thing, then the Lagrangian, which is transversal to this lambda 0, can be considered as a graph of some mapping from L0 to lambda 0, right? So you have anything like this. So maybe V is just a half-dimensional subspace, so that V is transversal to lambda 0. Okay, and then we can regard V as a graph of linear map from L0 to this lambda 0. Okay, so just like this. Okay, because and then we note that because both are Lagrangian, I mean the Lagrangian transverse each other, so therefore lambda 0 is canonically identified with the dual space, linear dual space of this Lagrangian. Okay. So maybe I denote this mapping like phi b. Okay. So this phi b is a map from lambda 0, L0 to lambda 0, and identify it with the dual space of lambda 0. So therefore, you can think of it as just a bilinear form on this L0, right? We can also regard it as a bilinear form here. So this is okay. But now I assume that this V inside of this R to N is a Lagrangian subspace. And then this implies that this bilinear form is actually symmetric bilinear form. So quadratic form. So therefore, the Lagrangian, which is transverse to lambda 0, is in one-to-one correspondence with the symmetric bilinear form on this Lagrangian L0. This can be anything, whenever it is transversal to lambda 0. But anyway, so you fix one, and then you can have such identification. And so the space of symmetric bilinear form is isomorphic to this, right? So therefore the complement is actually like this. And next, so this is one picture, right? So now, okay. So any Lagrangian, you can find such a coordinate neighborhood. Yeah. So if you have L0, and then pick Lagrangian which is transversal to lambda 0, and then consider this sigma, and then take a complement. Certainly such a complement is the open neighborhood of this guy, and it gives you coordinate chart, right? Okay. So now you have this L0, so it's a Lagrangian manifold, and then consider this thing. So here I use this another lambda 0, but here I consider this L0. But anyway, they are actually mapped to each other by unitary groups, so therefore the other actually can be identified. But anyway, consider this one, and then consider the intersection with that guy. So this is a kind of coordinate neighborhood of this point. So what is it? So this one is, we can consider it as a quadratic form on L0 because of this argument. Next, so this implies that it is one-to-one correspondence with quadratic form on L0, and then it is actually degenerate. Like this. So you consider the space of quadratic forms, and then consider only degenerate one. So I don't know how to really write it, but so in this space, you consider the space of quadratic form. It is just like a Euclidean space, but inside of this Euclidean space, you have this degenerate loci. I don't know how it looks like, but the complement is certainly open, the open-dense subset, and complement is actually corresponding to the non-degenerate quadratic form. So if you have certain generic point on this loci, so this is this thing, then if you take a generic point of this, then this is degenerate quadratic form. But because it's generic point, so therefore here actually correspond to the quadratic form, but dimension of the null space is just one-dimensional, right? So you have just one-dimensional null space. So here I have one-dimensional space, and away from this loci, non-degenerate one. So you have eigenvalue 0 somewhere, and one side of it, this eigenvalue 0 becomes negative, and the other side it becomes positive. So therefore, there is kind of co-orientation of this. Namely, you can just make this degenerate eigenvalue to -1, then you come to this side, and you move this 0 eigenvalue to the positive side, and then you come to the other side. And so therefore, you have such a co-orientation. Once you have a co-orientation, certainly we have bad singularity, but this bad singularity is actually codimension 3 inside of the whole space that we can show. And so therefore, if you have a path, then you can avoid this very bad point, very bad loci. So therefore, if I start from 2 points, yeah, we have a path, lambda t, which is transversal to some Lagrangian, then it is away from this one. And then I have path. Originally, it may pass through this, but maybe we can avoid it. And then maybe it becomes like this, right? Then this one is coordinate one cycle, which is co-oriented. So therefore, you can just count the number of intersections with signs. So this is a positive intersection, a negative intersection, and positive intersection, so on. Then you just add them all the contributions, and then you get some number. So that is a topological index. And this is very somehow related to this. So this is a topological index. Just look at this Lagrangian Grassmannian, and then take this reference Lagrangian, and if they have these two endpoints which are away from this sigma, and then you can do this. And if your starting point is on this very bad point, and then we can still get some integer as follows, because maybe here quadratic form is just 0, just completely degenerate. And then you just try to change it to a negative definite direction. So you just consider some smallest path, but a short path towards the negative definite direction, right? And then if your path is starting from very bad point to somewhere, and then just concatenate the inverse of this path from negative definite to this degenerate one, and then going around, and then still you can get some number. But anyway, so this is another story. So, and also, you may also, yeah, if you are here, then you may also count the contribution just half of the interior intersection. That also may be possible. So, but anyway, so there are some cases you may just consider such things like Salomon-Zender's, Robin-Salomon work. So anyway, we have this. So the end, in the end, what we can show is the following. So I have here two Lagrangians. Maybe here I may have this L of Z of tau, and here I have L1 of tau. And then we have a massive index of this, mu of maybe U star of Tx, and U R cross I star of T Li tau, say, okay, something like this. Sorry. Sorry, this is not true. This is not true. This is not true. So this is not true. This is just this. Okay, this is just like this. Because I pull back the bundle, so therefore here actually it is T to the U of tau 1 of L1. So it is actually kind of on different point, but anyway, just like this. So this one is an index coming from this. Yeah, maybe I only discuss one side, but we can also have both sides. So, and then we also have this linearity operator here, and this U. Okay, maybe U for this U, DD going to DD, not DD, but U. Yeah, U. Okay, U is a map from cylinder to the target. Yes, and then take this index, and then this one is equal to. It depends on the sign, but this is equal to mu of this U star of Tx and U of R times Zi star of Tli. So this is the index formula, and so then, but what I said is the following. So this one is equal to this mu of p tilde plus minus mu of p tilde minus, right? So this is the dimension of the space of solutions before modding out by a translation symmetry. So why is this? So now the story is, I mean, little bit, I think the story becomes rather nice. So here you have this cylinder, and then we have this U star of Tx and U star of Tli and so on as before. And this is actually converging to this P minus and this converging to P plus. Now I consider different domain like this. I don't know if this is good to write it, but anyway, I can write any picture like this, but maybe I can just write Z, something like it's a complex plane, in the complex plane, and then either this one is bounded by 1, or the real part of Z is non-negative, or real part is non-negative, and imaginary part of Z is in this 0, 1. Is it okay? Maybe not so good to write this. Maybe like this, or this Z, and the real part is positive, and the imaginary part is in this 0, 1. No, minus 1, 1. Sorry, like this. Okay, so just a half disk, and then do this. Maybe I have to just rescale it 1/2. But anyway, so we have this type of picture, and then so this one is a solution, the domain of the solution of Floer equation, and this one is nothing to do with such a geometric, solution of Floer equation. I just prepare some linear operator there. So here I consider following. So it's infinite, has infinite end. And here I take this T P minus of L1 here. And here I take T P minus of L0, because P minus is the intersection of these two. And then I take certain Lagrangian subspace starting from here, ending up with this. So I take something like lambda. I don't know how to parameterize it, lambda S. So lambda S is a family of Lagrangian subspaces joining this one, this one. So just consider such a boundary conditions. And then we can also consider the bar operator with this property. So this one I want to consider here, okay, and denoted by this. And this one is actually dt bar of u or something. Now, for each intersection point, I prepare such a path. Okay? So for each intersection point, I prepare such a thing. So I have this boundary condition and also such a Fredholm operator. And if I have this is a geometric one, so it's a linearized operator of the Floer equation, as I roughly indicated before. And then somehow we can glue them together as a linearized operator. So you forget about geometry, and here you have just a linearized operator, and then glue them together. Glue them together. And so then you get some operator like this, right? So this one is actually here, this T of U of tau T, tau 1 of L1, and here t of u of tau 0 of L0. But here I use just this lambda s. And here I just join them, yeah, just continuously, because this is actually always the converging to the tangent space of this Tp minus of TL1 or Tp minus TL0, and because this one starts with Tp minus L1, Tp minus L0, so therefore somehow we can just glue these conditions together. So here I have some operator just giving this boundary condition, and here it is coming from the geometry, pull back everything. But anyway, so you have such operator, and then on the domain, I just glue them together, and we can still make certain differential operator. So then I may write this operator like a d bar of this u and this lambda s. So I have three operators, and then the point is the following. So index of d bar of lambda s, this family, plus index of this dd bar u is equal to the index of dd bar, index of d bar of u and this lambda s, this operator. So you have some operator which is invertible at this end, and this is also invertible at this end, invertible at this end. Then actually you have such an index sum formula. It is a version of Atiyah-Patry-Singer type formula, but this is just a complex one-dimensional case, so it's very, very easy case. But so we have this index sum formula. Okay. Then somehow we can regard this as a path at p plus, right? So because I have a path, so here I have a t of p plus of L1, and here I have a t minus of L0. And then if tau goes to plus infinity, this one certainly tends to this, and tau tends to infinity, this one tends to this. So therefore, this path is very close to these endpoints are very close to this. So therefore, we can actually construct from this path some path like this. Okay. And maybe I have to say a bit more, but for the action, I take some covering, and then I denote p tilde plus or p tilde minus. And here, I'm talking about index, and our covering space also taking care of ambiguity of the index. So therefore, maybe I can take it p tilde minus here, and then the p tilde plus here, and then this is p plus here, like this, right? So what I want to say is, this one is actually mu of p tilde minus. So index of this operator. And then if you add with this index, then you get index of this one. So this one is index of mu of p tilde plus. So therefore, the index of the linear operator is written as a difference of these two indices. So that is the formula I wanted to say. This formula. Is it clear? So I wanted to explain this, how to assign this. Then I just use this analytic index to define this. So in this case, after I consider certain paths here, path of Lagrangians, and this path of Lagrangian is the information giving you this index mu p tilde minus and p tilde plus. And so then you can do this. And then we can also talk about topological index of this. And that is now you start from here to here. Then that is again a path. That is again a path like this, right? Because their starting point, the end points are transversal. So therefore, somehow, yeah, we have to little bit different situation from there. But still we can do something like this. So just consider this path and then try to assign some number by using this. Maybe I just tell you some story on Monday, but this is the way to, yeah, there is also another way to define this mu by a certain Maslow type index of this path. And okay, so this is a numerical things. And finally, I just want to tell you a bit about signs. And then I finish today. So signs, yes? I don't know, maybe 10. It's already 5. Okay. Then very briefly. So what we can show is the following. So if we have L, which is inside of this x omega, right? And then I take beta, which is a relative cohomology class, like this. And then try to consider this modular space of holomorphic disks first. Okay, and mode automorphism disk. Anyway, we want to consider such a thing. And then we want to give orientation of this. And if this one is transversally cut out by this d bar equation, then the tangent bundle is actually the family index of this d bar of u, and u run over this space like this. So you have a Fredholm mapping, and then if it is submersive, and then the inverse image to 0 is this manifold, and then tangent space is certainly the kernel given by the kernel of this linearization operator. So therefore we have this. And so we want to give us orientation on this. But in general, it is not possible to give orientation here. And then our idea is the following. Just briefly, and then I finish. So here I have a loop, like S1 cross DD to this X and F. So I have a family of things like W of theta or something. So theta is actually here. And then W theta is such a map. And then we want to consider family of such a d bar operator problem, so d bar of W theta things. And then how we can give orientation to this. But so this index bundle is over this S1, right? So theta is moving on this. So therefore, we have an index bundle over here. And the question is whether this one is orientable bundle, or maybe how to give orientation on it. And okay, so the key is the following. So okay. So now the question is the following. So you have this E and F, over this d2 and d2. E is now pullback of x and tx and pullback of t. And then let's suppose that f is trivialized. So you fix one trivialization like d2 cross r n or something. You just fix such a trivialization. So fix. So trivialization, if you have a trivialization, then from here we can give orientation on this index space. Yes, so dd bar v. So this is one key idea. And then how to, so in this case, how to give consistent family of trivialization. That is a topological problem. So anyway, you have a trivialization and you have this. Why such a thing is true? So I have disk here, and then originally I have this E and F. But because F, I assume I have a trivialization, so therefore, if I consider certain concentric circle here, and then we can actually trivialize a bundle E over here, right? It's a color neighborhood because F is trivialized. And then E, respect to the boundary, is also trivialized because this is just like this. So you can trivialize it. And then you can extend its color neighborhood. This is this picture. So now I have a trivialization near the boundary, and then somehow I just collapse this circle to a point. So this collapse this one to a point. Collapse this circle. Okay? Then what we get is somehow disk, and then I have a sphere like this. So here we can consider certain Fredholm operator. It's a D-bar operator on this P1 and D-bar operator on the disk, and the value coincide at this red point. So I have these two things. So one side is this, the other side is this, and then I have this and this. So maybe just I just write a definition of this, and then you can see it. So this is a problem, but I erase it. So okay, so maybe I just consider gamma of CP1 and this bundle E. Maybe over here I have a bundle E tilde or something, right? Coming E tilde, and consider the product with this D. But now it's very easy. It's a trivial bundle because I use trivialization to collapse this point. So everything is trivial over the color neighborhood. Therefore, this one, this. And so I consider pair of sections like Xi and theta here, so that this Xi is a section over here at the north pole, so the south pole, is equal to the value at the origin. So this is south pole, and this is origin, and this is equal to theta of 0. So we consider such a subspace. So just coincidence condition at this interior point. Okay. Okay, and then the target is just a product. The omega 01 of CP1 and E tilde, and then omega 01 of D of this Cn. Okay? Maybe I take the L2 completion or LP completion of this, and then we have this operator. So just operator is so cosinus operator here and coefficient operator here, and then restricted to this domain. And then I denote this operator maybe D of 1. And then by Grewing theorem, by Grewing theorem, this is a linear Grewing theorem, index of D of 1 is equal to the index of this original operator, D bar of EF. And sorry, so index. So for simplicity, assume surjectivity. And just regard indices are just kernel spaces. And then what is happening? So I consider kernel of this. So this kernel of this Lever operator on CP1 and E. Okay. And then I map it to this E of the south pole, maybe E tilde of the south pole. So I just take a value here. And from the other side, I have kernel of the bar operator on this Cn and Rn, just Cn and Rn. And then I can also map it to here, but this one I can identify with Cn, and then I have them. So these both are aberration maps at central point and aberration point at south pole, right? And these five are actually identified, so therefore we can have this. So kernel of this thing is nothing but kind of fiber product of this. And if you look at this is a trivial question, right? You have a Cauchy-Riemann equation with boundary condition on the boundary. It is always Rn. And then this one is canonically identified with this Rn. Okay. And this side is actually certain complex vector space. And so you have a complex vector space, certainly you have a certain orientation. And now I want to take certain fiber product over here. But if you look at this, then still the definition is not so nice. But we can actually consider a certain more stronger surjectivity so that this one is surjective. Namely, if you just add certain twist on this part, and then you can always make it transverse. And if you just make such a twist, it's also complex contribution. So therefore, even though we just do something, it doesn't really harm anything about orientation issue. So then I have a complex orientation space, and this one is just canonically oriented because I have a trivialization. That means in particular this one is oriented. And then I take a fiber product over a complex space. This is also oriented, so therefore this space must be oriented. So therefore we have orientation on this index bundle from if this one is trivialized. But this is not really true all the time. So I mean, it depends on trivialization. If you change trivialization, story changes. So I just want to finish one word. So maybe you heard of the following condition. Let L be not just Lagrangian, but also spin manifold. So if I take spin manifold, so spin manifold means that structure group is already lifted to the spin group, and the spin structure is actually choice of such lifting. And then if you consider two skeletons of this, with respect to certain simplicity decomposition, and then you restrict your bundle over here. This is almost trivialized. So in general, maybe I have to add one more trivial bundle, but anyway, this is actually stably trivialized. Just so somehow this spin structure gives you certain stable trivialization. And so then in the end, I just finished by this. I have this. And then I want to consider this W theta star of TL, right? This is a bundle over this thing. And I'm asking whether there is a consistent family of trivializations, right? But, so now you just restrict to the boundary. So this one is S1 cross D2 going to L, right? And this is 2 dimension. And this is maybe n dimension. But if you just consider 2 skeleton here, then by the cellular approximation theorem tells you that this one is actually deformed to this after homotopy, right? Because it's 2 dimensions, you can just do this. And here, the tangent bundle has trivialization. And using this trivialization, somehow you can put it back to here. And then you have a consistent family of trivialization here. So in this way, at each theta, this kind of orientation is defined, and so this is consistent. So therefore this one, as theta moves on S1, actually I get the oriented bundle. So this is actually the orientation issue. So therefore, we have to assume spin condition to get the orientation of the moduli space of the holomorphic disks. And in this case, we can also do the same thing because this part, if we have a family of solutions, this part moves, right? So U is moving on the modular space, loop in the modular space. But endpoint is fixed. So therefore, we can pick one, right? And also, we can pick another one here on the opposite direction. And then you can glue them together. And then somehow you can just reduce to this case. Maybe if somebody interested in it, I can tell you the story. So if you have a spin structure, and then you have orientation. And if Lagrangian is not oriented, still there is a notion of pin plus or pin minus, and then some of the argument can be go through. This is basically due to Jake Solomon, I think. But anyway, so this is the argument. And so in this story, if I want to give orientation index of this, what we do is just pick orientation on this part. So pick orientation on this part and orientation of this part. Right? For each P, I have this, and then I pick orientation of this part and this part. And then if you glue them together like this, and then this one is same as this. Okay? So now I have an index here. If you sum them up, I have this. So now I have one fixed orientation, I have another fixed orientation. Therefore, we can say that this kind of sum of the index and this one gives the same orientation or not. If it's the same, then we just count it plus 1. If it's not, it's minus 1. So this is the way to give signs. Somehow, I have to say the shifting symmetry a bit more, but somehow basically you give some information from here and here. And finite dimensional mode theory, the orientation of the index over here can be interpreted as an orientation on the stable manifold or unstable manifold. So that I mentioned before. So the finite dimension, you have such a picture, and if you just reinterpret it in this index story, and then you can extend it to this, provided this Lagrangian spin. Okay, so
this is for gravability condition on
orientability is gradability. The gradability. So gradability is this is the index thing, right? So gradability is, I think this is a little bit different. So you're talking about gradability, right? So gradability is something like this, right? So yeah. So yeah, I know. So you have this. First of all, you need some condition for the manifold. So you have manifold X, and then each point P, you have a Lagrangian Grassmannian of this thing, right? And then you take a union over this. So that is actually Lagrangian Grassmannian bundle of this. Right? And then the first question is whether you have a fiber-wise universal cover of it or not. And that is something to do with the first angular story. Right?
So it is stronger than spin condition. Because spin condition is a Z2 condition. This is a Z condition.
Yeah, this is actually Z2 condition, yes.
No, this is a Z condition.
Yes. So the liftability of this one, yeah. And yeah, that's true. Yes. But what I didn't really answer your question so precisely, so quickly, is that here actually what I said here is actually spin structure, right? So the manifold spin means it admits certain spin structure, right? But so the manifold admits finite many spin structure, for example, H1 of L of Z2. And if you change the spin structure, then this orientation of the moduli space changes. But for this one, actually, if you have this kind of Gauss map, and then ask whether this Gauss map is lifted to the fiber-wise universal cover or something, right? That is actually sometimes people may call it gradability. And so I don't know, so spin condition certainly vanishing of W2. But we really need to pick spin structure to really discuss something. So certainly related, but maybe to really give a sign, actually we need this. And lifting, maybe, I didn't, maybe.
According to physicists,
Yes.
condition for orientability is the gradability condition.
Yeah, but then somehow you may have some manifold over which this one has no fiber-wise universal cover.
Now, as long as when you restrict on the Lagrangian submanifold,
But if you don't have this fiber-wise universal cover of this guy, and then to which space you want to lift it up? So you have maybe I may be misunderstand your point, but so you have L here, and then here you can just map it Lagrangian Grassmannian of this X. So just a union of.
this particular map has a
No. Then you want to have this thing, right? And so here, this is the bundle over X, and here you have this UN over ON here, and so this is just a fiber here, and then what you're talking about is UN over ON, and then take its universal cover, right? And so what I'm saying is, this thing may not exist, right? the existence of this one is not
It's always exists because you can't define it otherwise.
No. So locally you can always define it. But the point is whether you can define such a thing globally. I think for instance, certainly in fiber actually, it is actually, you have a fundamental group. But so you have a fundamental group here in the fiber. But this loop maybe null homotopic in this space, right? Because if you have just you have the hop vibration, and then the fiber is S1, right? And then here you want to take a covering, this kind of universal covering like this. But there is no way to make any covering like this, right? Because this pi 1 of this is non-trivial, but image is actually trivial. So therefore you cannot really extend this kind of fiber-wise covering to this. So yeah, I'm worrying about such a thing. So in general, certainly you have such a kind of. Yeah, maybe we can discuss it later. So once, in this case, once you have such a structure, and then what you're talking about, whether this Gauss map can be lifted to here or not, and this is what you call this grading structure, right? And once you have this grading structure, so you have two different, you have two Lagrangians, then you can consider this lift, and then from there you can also define this index. That's true. So this kind of index can be also obtained from such a grading structure, yes. So grading structure is good, but sometimes. Yeah, sometimes we may not have this, and then such a lift doesn't really make sense. I think something like this. Yes, something like this. So like C1, if C1 is 0, then you have this sort of stuff, right? Maybe I can just try to do it a bit more.
Maybe we can finish and then we can.
Okay. Let's finish it. Okay. I think this thing, right? So UN and UN, and you have this determinant going to this U1. And so
if X is, for example, metacratic,
yes. Yeah. So right. But the point is somehow, so you have this, it induces isomorphism on pi 1, right? And so you have this Lagrangian Grassmannian here with this X. And then maybe we can also consider certain circle bundle over here. I mean, I have P of X, and this is actually a unitary, right? Because this is a symplectic group, it has maximum compact subgroup here. And so then Lagrangian Grassmannian is certainly P of UN over N, right? And then here again, we can consider P of UN times determinant of U1 or something. Maybe determinant square or something. People may consider this because this one maybe has two components. And so I think the fiber is actually UN or N, and fiber is this.
So you only need subspace to lift.
No, if you don't have this, where do you want to lift?
Oh, I think NP. This group.
But metaplectic group is a double cover, right?